Good morning. Dzień dobry. Good night for me. Just before I start, just wanted to tell you that we are 9 hours apart. So you can see the fact that day and night are affecting the longitude. And I assume that some students are attending, and will therefore I prepared some stuff that is appropriate to a little bit introductory level. And my topic generally is analysis of effects of the terrestrial aurora, and how can it affect, how can we, with an analogous manner and some insight, to go into other aspects of space and astrophysics. And therefore, I will start first presenting several observational aspects, just to give a general description of the essence of plasma physics in space, in our heliosphere. Okay, so the question would be, what can we learn from aurora observations about processes at similar magnetized configuration? And what would be the implication of the heliospheric anomalous ion isotope abundances for the so-called birth and death of stellar systems? It's a little bit general topic, and I will surely talk mainly about aspects from the aurora into heliosphere, into some processes of sun, specifically for observations of particular unusual abundances of specific isotopes. Okay, solar system, as we know, is completely is well known. The planet encircles the central star. It includes planets, dust, and many other things. A huge amount of electromagnetic energy, and asteroids sometimes, and other celestial bodies. Here's just for the basic description is how the solar system is the first satellite planets of the sun, of the solar system. What is interesting, and it's a general astrophysical phenomenon, that vast majority of the system are the planets are lying in the ecliptic plane. The same applies to the exoplanets, which is the latest topic of importance in research. Here is a beautiful description from our galaxy. These are stars which follow the same elliptic trajectory like our planets around the sun. And if I concentrate on some specific one, you can see that there must be some mass which controls their motion. This is essentially first direct observation and proof of the existence of a black hole. So the same physics applies to planets, to stars. On the right, you can see some of the orbits. Some of them are very interesting. They even relativistic and even quantum dynamics is involved because of the huge masses that are in the picture. I will go further. Very clearly, the same way, Bohr model of the atom is based essentially on the similar aspects as we saw for the big scale. And here I start first time entering into the plasma. So essentially what happens that as is in most of the environment, once electrons which are encircling the atoms acquire some energy, they become free. They go beyond the bounding energy of the nucleus, and we create new style of matter. This plasma, essentially, it's like a liquid, which is controlled not by van der Waals forces, like in regular water or liquid, but by electromagnetic forces, which bring also huge amount of interesting mathematics and physics due to excitation of variety of waves. One more general, still basic story from the Mendeleev table. We see usually the elements and see the number of protons usually is the reference for them, and also the total weight. But now I would like to add something else, which will bring me later to my story, isotopes, which are the same elements, but with different number of neutrons and different number of neutrons. Here are some few examples. And what is also important, the possible charge states. So helium at the Earth is usually almost always appears as an ion of +1, but at the Sun, at the universe, when it's more energetic, will be always almost always will appear with +2. And then there's helium itself has this additional isotope, and etc. Here is the first picture of aurora. The lines that you can see are essentially describing a magnetic field bounds that along them electrons, accelerated electrons flowing, as we see them only at a relatively low altitude, because then the density of the background plasma is already high enough such that it excites the atoms to higher level, meaning the electrons are jumping to higher level, higher Bohr level, and then they emit lights when they jump back. This is a well-known process, although quite intriguing, because some of the transitions are transitions which are forbidden by the first order transition possibility. The number is calculated generally from the amount of energy that is absorbed, the radiation which is seen, and converted into the original energy. And this is about the amount of the power station which is operating either nuclear or gas or any other method. Aurora from ground and space, just two pictures. You can see that the magnetic field are very clearly described. And this from space, we can see the oval, auroral oval, which will be seen also in other circumstances. Here's a picture directly from faraway satellites, and you can see this is the North Pole, and And there is all this area are areas where the electrons are hitting very strongly the plasma of either oxygen or nitrogen. Here is the first explanation of aurora, 16th century, and very clearly I would be interested to know what is the city which is shown there, and clearly there are some nice story about candles, and you can think that they knew quite a lot because these candles are, in some sense, magnetic fields, although they were not so much aware of this. You can also see some angels if you are a little bit with some imagination. Okay, magnetized plasma can be depicted, surely we can see in aurora, also in the sun, in the corona. I will talk about it a little bit later. This is the general description of magnetosphere. And aurora is essentially specific area. It's this generally this area of the magnetosphere. This is the magnetotail. The nomenclature comes from many years of investigation, and solar wind, which comes from this side, is impinging. When it's stopped, it causes shock wave, permanent, which is the bow shock. These are the picture of magnetic fields, and this altogether, this is very important for transformation of information through the atmosphere. That's Jovian magnetosphere, which is the largest object of the solar system. Very interesting. It looks not much different from our planet. It's essentially, it's much larger. This magnetosphere is much larger than the sun. It rotates with a 10 hours period. And if you go to astrophysics, there is something similar, which looks very similar to this, except that it rotates with an enormous speed, which is a fraction of a second. Essentially, some of them are milliseconds and even faster. So therefore, this plasma rotates so fast that at some moment it reaches the light cylinder. And this is very interesting topic in astrophysics pulsar. About Jupiter, yeah, I can look at this as a slow pulsar, which is looking this, the aurora itself is very similar to here and like at the Earth. And every time one of these three, for instance, this example, moons comes by and perturbs the ionosphere, it's connected to the field, and I mean, not precisely causes such a perturbation that once again elements of the lower atmosphere are excited and emit light, which is also our similar to our aurora, except that here the amount of energy involved is significantly larger. Saturn has similar story. Source of the plasma is Enceladus, one of the moons shown here. Ganymede is one of the moons, of Jupiter, and it has its own magnetic field. Therefore, you can see also the aurora. So this is almost a universal phenomena. Whenever there is a dynamo which creates magnetic field, there will be some kind of aurora. And solar in the corona for sure can be seen clearly as a set of magnetic fields which are rotating, and perturbation of them causes major perturbation on Earth too, which is very important topic by itself. Okay, some basic plasma physics. Electrons and ions which move in inhomogeneous magnetic field. As a Hamiltonian system, this is three-dimensional system, so there must be three adiabatic invariants, three canonical variables, and we can split them very neatly into motion along the perpendicular, rotating perpendicular to the magnetic field, which can be either static in some when it's constant, or moving slowly along the magnetic field. This rotation is very crucial. It's called gyro rotation, gyro motion, and the value of the time scale of this motion is given by charge magnetic field divided by MC. So what is important is that changing the charge or changing the magnetic field, the mass, immediately will change the time scale of this motion. There is another motion, which is described here better, when the magnetic field is inhomogeneous. Particle on top of the gyration also performs bounds. When it moves in this to the stronger magnetic field, there is effective force from stronger magnetic field into weaker magnetic field, and this force slows the particle in the parallel direction, but it doesn't change the energy, so it acquires V perpendicular. Then finally it bounces back and performs this motion when there is no perturbation. So this is the second, and the third one is drift. And so this is on top of these two, it drifts around this planet. In this case, around planet. What is interesting is that these three are very different in time scale. This is usually fraction of second. For ion is perhaps few seconds. This is will be few minutes, and this one will be few hours, depending on the energy. And as always, it brings into some interesting mathematical problem when you can split the time scale into sub-time scale and deal each one of them, each motion semi-independently. And that's why we have the notion of this adiabatic invariant, which are strictly speaking preserved for perfect motion, that they are violated by any perturbation from outside. If these adiabatic invariant are a little bit perturbable, this essentially can bring to an energization of particles. And moreover, when there is energy, when there is wave, external wave or emitted self-consistently waves, electromagnetic wave, they can exchange energy between them, between the waves and the particles. Here's a nice example of particle which moves, gyrates, bounce, and drifts. And what is unique about this, that this is a great example of trapping of ions and electrons in this time geomagnetic field. In geomagnetic field, we can also go into artificial field that we can buy, we can build, and this is the essence of the future energy input, and the famous ones, how to contain a plasma, bring it to very high energy, and with deuterium and tritium, for instance, start nuclear reaction and extract the energy from outside and bring it into current and power into cities, for instance. So this is the essence of the tokamak, which was started during the Cold War in the 50s. That's by Russians. That's why it has a Russian name. And Western ideas were started with Stellarator. Eventually, everybody is using both of them. Tokamak is much simpler, but it's a little bit more difficult to contain the plasma inside. That's why the most very complicated magnetic field of Stellarator is devised as a future project. At this moment, it's my small detour into fusion physics. The main reactor, which was in Stellarator, in tokamak in United States, was in Princeton. You can see the picture. And now this was the system that it included all the fields, currents, and supposedly confinement, which doesn't work that well. I remember that when I was a student many years ago, every year I heard the story that next year there will be break even when the amount of energy that we input will get it from nuclear reactions. And I think that only a year or 2 years ago, once I heard officially that we reached this point, but we still have to go above it. This is the construction of the ITER tokamak in France. And here I have some amazing pictures, which I would like to share with you. And these were done before the pandemic. So I'm sure that they are now much more advanced. Here again, Aurora is a laboratory for magnetized plasma with many interesting aspects. Now so first about the Aurora measurements. We in Berkeley, we built essentially the whole satellite about 30 years ago, small satellite, which went to cross the auroral field lines and was able to measure in fantastic accuracy and resolution particle distribution and waves. This is the general complicated picture of the results of our understanding of Aurora. Just because there is not enough ions to hold the whole current to make a circuit from the point of view of electromagnetism, there must exist in this area some region which has quasi-static electric fields. And first, some big perturbation in the tail of the Earth, of the magnetotail, which I showed before, it causes flow of plasma, and then the specific electric field which is formed here, which we understand it quite well by now, accelerates the electrons which hit the lower part of the ionosphere and forms the aurora. And this is the picture which we have and refine it over the time. The bottom line of my talk is that this phenomena which can happen here, we can learn from this something very interesting in other environments. So first, what we see really, observation, we see suddenly beam of electrons changing, surely, but quite strong, about 30 keV, moving along the magnetic field of the aurora. That's the observation visually. That's in situ when the satellite crosses the aurora region. And we have the electron beam, which is moved somehow here. This is the electron beam here at this point. Waves, observation of waves previously were very, what is particular, that every time an electron beam appears, there is also activity of waves, which is between the gyro frequency of hydrogen and the next ion, which is here was helium plus. And these are the waves which are observed all the time in the aurora region. The question is, why is there some element in the Mendeleev table that has gyro frequency between these two? This will be the first question. And the answer is very little. There is one element, which is helium-3. It has charge, the same charge, but mass smaller. So it will be here, but it's not observed at the Earth. There's no helium-3, just the effect of life. So the picture in the visual terms would be, if we took at the gyro frequency, you see the mass is the variable, and at the terrestrial aurora, we have hydrogen, helium, oxygen, and the waves are somewhere here. It's surely different from the solar corona. Here are the observation of really of waves, and you see that the electron flux is modulated by this so-called electromagnetic ion cyclotron wave, which the ions are emitting themselves, and the electrons are emitting, which flow along the magnetic field, and therefore I would like to say just a very general statement about the approach to plasma physics. This is essentially whole course. I will give it in 2 minutes. So what is done, we couple the set of Maxwell equations with either Boltzmann equation or fluid equation. This depends how accurate we want to describe the distribution functions of the particles, either in phase space with places and position and velocities, or you already integrated over velocities of each particle, and get it all in macroscopic quantities. The bottom line is that if we split the variables space and time, we get a perturb. We can perturb the linearly the big set of equations, which I will show in the next view graph, and the set of the consistency of the equations brings some specific result, which is called dispersion relation, which gives essentially the relation between frequency and wave number vector. And the exchange of energy and momentum between waves and particle occurs according to this equation, which is essentially very straightforward. It says that the particle which sees frequency, which is Doppler shifted, frequency of the wave, which is Doppler shifted by the wave. The frequency which is Doppler shifted by the motion of the particles and its rotation around the magnetic field. There's also correction of relativistic. It sees the same electric field of the wave and that's why it's either accelerated or decelerated. In more detail, this is the Vlasov equation of collisionless plasma, Maxwell equation, and if you solve them, I'm jumping here to the result, the perturbed linear waves immediately appears this kind of denominator. And therefore, I already described it before. And when the denominator is very small, there is strong interaction between particles. And here is the essence of this is so-called the Landau damping. That's the interaction between waves and particles. When the wave, this is without magnetic field, when the wave is moving along this direction, and particle with phase velocity, frequency over k, and particle is moving with its velocity, it's wave surfing, and there is unmagnetized dispersion relation, which shows this. Magnetized gives this relation when the gyro frequency appears naturally. And here's example. So these are, let's say that this is electron in a wave, and the wave is exactly with the speed of the electron, and then the wave itself always has electric field, and that's why it can accelerate the electron very easily. And this is a major process in which energization of ionized particles occur. But what about ions? They also have, but they have different appearance. And ions have also different charges and different masses. So that's also can appear. So this is the analogy. I will stop for a moment with plasma because I enter now into the essence of the enhancement of isotopes due to plasma processes. This is, by some people, is considered one of the most important graphs, plots in physics. Big Bang nucleosynthesis, and as we understand it, 13.6 approximately billion years ago, there appear mainly five elements with additional. Besides hydrogen, this is abundance versus essentially the density of matter. This is Hubble constant, and this is a specific quantity which is relevant to the density. So we have helium-4, and we have deuterium as a function of this quantity. We have helium-3, the isotope of helium, and lithium-7. Each one of them has fantastic story to tell. The same happens here. Here it is as a function of ordinary matter, meaning bosons versus photons, ratio of bosons to photons. And the most important point is that this abundance essentially must give the original density of baryons of matter. And since we understand extremely well the cross-section at these high energies, we can easily conclude what should be for instance, the density today of the baryons in the universe. And this is the argument why the baryon, which we can observe, which have interaction, electromagnetic interaction also, is about 4% of the full density in the universe. And we know that the rest is energy and matter, dark energy and dark matter. So this is the introduction for this purpose. What I want to stress is that the ratio between helium-3, the green, and helium-4 is about 1/4,000, 1/5,000. And this is the summary of the primordial nucleosynthesis, that it depends on these three conditions, which are extremely well known now, except of this ratio. And this ratio determines essentially what should be the abundance at the beginning of the universe. How does it related to us? So here's a repetition of the same process with a nice picture of the isotopes. And this comes now the question. Over almost 40 years, now there are measurements of solar anomalous abundance here. And we see in many events, due to so-called impulsive flares, that helium-3 is enhanced versus helium-4. While the original value was 1/5,000. It's one of the biggest enhancements in heliosphere that can be observed of any kind of two elements. And why it doesn't happen in any other of these elements, or any other isotopes and elements of due to evolution of the star. So here is first again general observation that although helium-4 should be 5,000 times larger than helium-3, it's clearly they are almost of the same order or a little bit smaller in these cases. The previous case, which I showed, is a little bit unusual. But we also observe in some solar flares that not only helium-3, the red one, is larger, more abundant at helium-4 in high energies, but also something happens with the iron and oxygen. Generally, oxygen is the green, should be about 10 times more abundant according to evolution of stellar evolution. And here, two examples that the iron is more abundant. So, question, is there relation between these two phenomena, that iron is and helium-3 is more abundant? That's important question. Here is one example, also relatively old already, of emission of each particles which is emitted in the flare and arrives at the satellite is observed. So each dot is a particle. And we can see that there is at least this event, helium-3 comes, it goes faster, and then comes iron at the same time. Supposedly they were observed at the same event. So the summary of this part is that in a Big Bang, helium-4 to helium-2 hydrogen is about 25% by mass, which is important number. Helium-3 to helium-4 is very small, 1/5. Should be 5,000 if the zeros are correct. But impulsive flares it's very often larger than 1. In stellar evolution, iron to oxygen is 0.1. In passive flare, it's about 1. Okay, I would like to stress few plasma parameters, which is plasma frequency, which is the oscillation, natural oscillation of plasma when you don't have external perturbation. Gyro frequency, we already saw it, and beta of plasma, which is essentially the pressure, thermal pressure to magnetic pressure. And these are the 3 parameters which characterize every plasma phenomenon. Important thing, in solar corona, the beta and is of the order 0.1, 0.2, same in the aurora. The ratio of plasma hydrogen and the gyro hydrogen is very similar in both of them. We know that in the aurora, we have intense electron fluxes. We see them in situ. And we know that in the corona, we have them because we see X-ray, meaning there was some, along the field line, there's a lot of Bremsstrahlung. Surely when they arrive, the electrons which flow here, when they arrive lower, the density is very large, you can see much stronger emission of Bremsstrahlung. So altogether, these two entities, corona and aurora, each one of them have completely different values of density, magnetic field, etc. But the basic parameters which control plasma effects are very similar. So this brings us to the idea that since we observe here very well the aurora, we observe remotely the corona, perhaps the phenomenon is similar. There's one big difference, that here we have the waves, we see them waves on satellite. Here we assume that the waves exist. We cannot reach the in situ. But here we know that there is helium-3, and here there is none, almost. So the picture of the physics will be that electron flux flows along the field line in both of them, excites waves with some wave number oblique to the magnetic field. And there are particles at the corona or the aurora, which are in the magnetic field. There is a small pressure gradient between the stronger magnetic field and the weaker. So they move slowly and fill the field line. Why, when the wave comes, it has its force due to the wave which is excited here. Its force affects these particles, provided that they interact with them according to the plasma conditions, that the phase velocity will be the phase velocity subtracted by Doppler shifted will be the velocity of the particles. But what are the particles in the solar atmosphere? They are, I emphasize, helium, iron, krypton, and xenon. I will tell you why I specified them. But they move, they are affected, they can be affected easily by the wave. And there's helium-3, surely. So the picture is that there is the main element in the solar corona will be hydrogen, helium double plus, oxygen ionized many times 6 or 8, because it's a million temperatures corona, and iron and many other elements. And the statement which we suggest is that high energy helium will be affected directly by the electromagnetic waves, meaning helium-3 falls exactly at the region of the waves, and that's why it's affected. While all the other elements, which are almost fully ionized, will not be able to, because they don't satisfy the condition, while iron partly is able to satisfy it. So here is the abundance which I created many years ago with very provisionary graphics at the sun. So here is the gyro frequency, normalized gyro frequency to hydrogen, and we have every element which exists, but only the one that fits the frequency of the waves will be affected strongly, and this is the helium-3, such that helium-3 is the magic element which all automatically can be accelerated. Surely this depends on the temperature of the elements. As we change the temperature, the structure, abundance of the other elements, background, will change. For instance, at 6 million, the previous one was at 4 million. At 6 million is already, there will be some isotopes of iron, which also will be able to interact in the second harmonics of the wave. Other elements will be affected much less. So at 10, iron will be so effective that I can declare specifically that that this is not able to feed the data, because there will be a huge amount of iron, such that the observation also can give me some information. What is the temperature of the corona? And this is quite important. Some quasi-analytic statement that if I choose the equation of motion of helium-3, and the parallel propagation is given by wave force, which wants to push it down, and mirror force, which is the gradient of magnetic field, which wants to push it up. And the result, if they equalize, clearly the solution will be exponential growth in perpendicular energy. So it means that particle first, when it encounters, it goes up, then it starts being affected by the wave force, slows down, and then as it stops, as it becomes very small, then it very much accelerated. Here is the simple simulation of particle. Parallel velocity goes up along the field line, encounters the wave, starts oscillation. Beautiful mathematics can be done. Finally, when the energy is so big that cannot satisfy anymore the interaction, and it's ejected out. And the same for energy and for position. I have several examples of this ion going is affected by helium-3 is affected by the waves. And the same applies to iron, but it is much similarly looks. This is the data, And then the question is, are there any other elements? And the reason for this question is that there are some ultra heavy xenon and krypton, I will describe it, that are observed. I don't want to go into this picture, but you can see it's beautiful data observed that in the region when Z is 70 to 80 or 50 to 56, there are some big increase in abundances. Or in other words, this is a summary. It's called ultra heavy. Is that these are the between 50 and 250 weight of element. There are several regions when it's excited, enhanced abundances in this solar flare, impulsive solar flare. So this is the iron group. This will be the xenon, I think, and this is the krypton. And here it's something additional, not so clear. So I don't know what is really happens there, but having already done with helium and the iron region, my statement was that higher harmonic resonance with them is causing it. There are some other turbulence model, very complicated, and this is still in debate. So I hope that we agree that Aurora essentially is quite an excellent laboratory for plasma processes. But now it brings me into uncharted waters. I want to say something in a few minutes about aluminum-26 as a clock for early solar system. So first of all, in the galaxy, aluminum is second most important illumination in the Milky Way. It has 1.8 MeV, very strong in our galaxy observation. What is special about this? If I jump to nuclear physics, magnesium, they are measured different minerals in meteorites. They show excess in isotope 26. And the only way to get magnesium 26 is from aluminum 26, radioactive aluminum 26. That's why it is observed there. And this is enhanced in the early solar system. So what I mean is that in the meteorite, in the galactic ratio, in the universe, in the Milky Way generally, what we see, the ratio of aluminum 27 to 26 is 3 to the 10 minus 6. While I will describe in specific meteorites, the ratio is much higher. So there is some reason that there must be some excitation, enhancement of aluminum 26, and it will decay into magnesium 26. The story is much more interesting. Here is in 30 seconds, the class of meteorite physics. There are the primitive meteorites are the chondrites. In them, there are chondrules, which is the standard one, molten silicates. And there's the calcium aluminum inclusions, which are specific refractory minerals, which are evaporate very last. they reach high temperature. They are also oldest. I will show you immediately the point of this. And aluminum, which is isotope, it goes into magnesium excited, and then which excite the 1.8 MeV with a half time of this, 0.7 million years. And therefore, the observed excess of the decay product of magnesium in calcium aluminum inclusion provides some record of the original aluminum 26. So I think that I went far away from my story of plasma physics, but there is some phenomenon which creates excess aluminum 26. Must happen more to 26 because we see that in specific meteorites there is magnesium 26, which cannot be obtained differently. In the isochron, with the controls, they find the time when it was formed, 4.564 years in millions, and while in this is 4.567. So this was a little bit earlier. It's amazing accuracy. And in Allende, this is typical picture of, you can see the calcium aluminum, and measure from these different measurements of magnesium 26 and aluminum 27, which are stable isotope. From the slope, we can find, people find these specific ratios which are unusually high versus galactic values. So where does it come? There are two possibilities. There's either external nucleosynthesis event, which is proved insufficient. And this was the major problem, because if it happened just for us at this moment after formation of the solar system, then we would see also many other unusual ratios which we don't see. So my suggestion was that the copious X-ray activity which specify young solar system is related to intense helium-3 energization. And here comes the point that there are three fantastic energetic interaction. When helium-3 hits stable magnesium 24, magnesium 25, or aluminum 27, the result is aluminum 26. Bottom line is that aluminum 26 abundance is increased before solidification due to interaction with energetic helium-3, resulting in magnetic magnesium 26 inclusions in the calcium inclusion. I wanted to say something about astrophysical helium-3 problem, but the time is already exactly, I reached 1 hour.
Well,
so,
you can please go on, Professor. Please go on with that.
I thought that I'm limited to an hour. Okay, so I will do it relatively fast. At the end of the life of a star, it's either exploded, or if it reaches RGB, this red giant level evolution, it emits its mass eventually, most of its mass, and it's shown in this kind of feature. In 19th century, when people saw it, they did not know what's that, but it reminded them planets. So that's why they call it planetary nebula. And this is a topic which is a little bit tricky for many people, for me for sure. So I will just describe it in a little bit in hand waving. There are not many of these observed extremely well, but there are some fantastic observation of this planetary nebula. So the question is, what can we learn about the evolution of the stellar evolution with respect to helium-3? People ask themselves, can it be that the helium-3 is a cosmological barometer? What means that it can tell us really what happened in the time when the sun started was reaching its final level of existence. So if we go understandingly into the evolution of elements during the burning of star, which is most of them, all of them that have mass more than 8 sufficiently large mass, larger than brown dwarf, so-called, it's nuclear reactions started in the sun, hydrogen is burning, and then other elements are burning also. We understand it quite well. So abundance of helium-3 should increase in time and be higher in the region of stronger stellar processing, or in other words, closer to the galactic center. That's first statement. Now, helium-3 can be observed only, I will show you momentarily, one way, only due to some spin flip of 3.46 centimeter with a hyperfine transition at the atomic physics. And the observations which we see are the following, that such effect does not exist. So there is some problem. One, there's additional problem that generally that they observe in most of the abundances ratio of 2 to 10 to minus 5 of helium-3 to hydrogen, which is the standard value. But in the planetary nebula, which are formed from the red giant phase, and they encompass a hot central star, they find that this ratio is even 10 minus 3. I think I saw it first time some 10 or 12 years ago, that they call it astrophysical helium-3 problems. Or in other words, there must be additional process, must be required to enrich helium-3 in planetary nebula, provided, according to the evolution of stars, it happened in the low mass progenitor star. Progenitor is the original one. The low mass, it was about less than 2 solar mass. So the story is that there is some problem, but we can solve it if in the low mass star we shall find some way to do it. And people did it. I will not go into details, only will tell you that the measurements of this transition, the hyperfine transition, is done by probably one of the biggest devices on Earth. I cannot remember the weight of this, but you can see the style. It's in the Green Bank telescope. It's humongous, huge. And the observation takes huge amount of hours, thousands of hours. And finally, this transition, this gives the value that the astrophysicists were looking for this. So they could not. They tried to find something very complicated with burning at the level, the outer level, and I don't want to go through this. I wrote about it something once. The point is that finally, when they measure it, they found that the mass of this was not below 2, was above 2. So this is not working well. So my solution, probably, which is a suggestion, that hot low mass stars on the main sequence are expected to be very convecting. Therefore, dynamo is working hard and they will be magnetically active. They have very frequent flare occurrence and are able to enrich substantially the nebula in helium-3. So this is a wild suggestion, but that's my status of my story. And again, going to the summary, Aurora is excellent laboratory for plasma processes to explain today observation in the heliosphere, in the sun. They also are good for something that happened 4.5 billion years ago, and maybe 4.5 years in the future, and surely today. So this is the story, birth of solar system. Some you can see on the left. These are the explanation of this enhanced emission. And on the right is a famous planetary nebula called Cat's Eye, that maybe is some effect is related also to our solar flares or essentially aurora. Dziękuję.
So thank you very much, Professor Ilan Roth, for the presentation. So please have some questions and comments.
Also, thank you very much for a great talk. So regarding helium-3, I know that there are also these problems with abundant amounts of from volcano earthcrafts. So I think it's not well understood where this helium-3 comes from. So I think that there are some problems with understanding of nuclear processes in this scale. Another question is that you have mentioned at the beginning that there is some quantum processes at this macroscopic scales. Could you elaborate here?
Okay, so first about the nuclear, yes. Years ago, when I and my collaborator, when we essentially were sure that this is valid argument comparison between Earth, Corona and Aurora, we called Air Force and asked them if they can plant a lot of helium-3 ions in the ionosphere, that they can inject them there. It was crazy, surely. The answer was that helium-3 is used in other fields, and there's nothing. So we wanted essentially to make analogy between the solar corona and Earth terrestrial aurora by adding what is missing at the Earth, and it did not succeed, but surely. But this is essentially nice story if it would be possible.
So I know that there are problems with helium-3 because, for example, one of the main sources are thermonuclear missiles from Russia because of tritium decaying to thorium-3, and it is used especially in the neutron detectors and the gates to check if there are some nuclear materials. So after 9/11, there was a large need for helium-3, and there is some problem with availability, especially for the freezers to get nanokelvins. I will say that they're required. Helium-3 is very low.
I cannot say too much about it. I know that essentially we understand helium-3 is needed for other purposes, and nobody will give us this. Although there are some stories, there are some possibilities maybe, and I'm not interested in this now. I got interested recently a little bit more because in Bern in Switzerland, they are going to have special workshop about what is new with helium-3 acceleration at the sun. And there are many new data. Nothing that will change my story, but there are a lot of extremely interesting processes. It comes out that every time something like that happens, when you see enhancement of helium-3, you also see jets of plasma, and etc. So the bottom line is, next month there should have been the conference there. So that's why I got interested. But from my point of view is the story about the past, future, and present. And somehow, so yeah, I chose these specific nuances where helium-3 is observed. I didn't add that in the planetary nebula, there's also enhancement of carbon-13 versus carbon-12. So I don't know really. They don't have explanation. Don't have good explanation. But maybe, once again, the mass 13, 12, small change. One of them can be affected by the waves because they are at the right spot more than the other. Maybe.
Yeah. So this small change, carbon-12, 13. I know that in plants there are some plants. There are two types of cycles in plants, and one has better selection for this carbon-12. So for example, if you live in America, you have more carbon-13 because of using this corn, which has more carbon-13 because of different cycle of, yeah.
But this is, I think, you talk about chemistry now.
Yeah, yes. So there are some specific. Yes.
I did not tell you there's beautiful mathematics which I skipped. For instance, the relativistic effect. It's very important. I put the gamma, if you remember, at the resonance condition. Omega minus n gyro frequency divided by gamma equal kV. The gamma, as a particle is accelerated, the gamma is changing. As it is changing, the resonant condition is modified consistently. Quite beautiful. And thanks to gamma, the helium-3 and iron and others can be accelerated much more. Although all these particles are non-relativistic. And this I find it also quite interesting. Particles which are completely non-relativistic, far away from, but resonance is very sensitive to velocities. And therefore, the interaction when the electric field is punching all the time in the particle and accelerating it works well. So I found it also interesting. Now you ask me about quantum physics, and I probably should tell you that let's discuss it some other time.
Sure. So I will give a talk this Thursday about. So there are. I believe that there should be some quantum-like phenomena in there. Oh, there is a question.
Yeah. But, okay. I can give several answers, but I also look at the time, and this is here. It is 1:17.
So maybe
Okay.
come on my talk Thursday. Yeah.
Okay, so we have one more question from Łukasz Pluszyński. Please move on.
In case of the astronomical aurora outside the Earth atmosphere, have there been project of using the probes to check the exact parameters of aurora of, say, Jovian aurora?
Sorry, UV aurora, you ask?
Yes, have we checked, have there been the idea of checking out the aurora of the other celestial bodies?
So, I skip, I touch many topics. Generally, the aurora that we see with naked eye is absorption of electron comes close to the atom of nitrogen or oxygen, exchange some energy, electrons in the bound come to higher, and then after some time, not immediate because it's forbidden, they fall back, and this is the light that you can see even here on the picture. I don't know if you can. My first one, the
Yes.
beautiful aurora which we see, either of oxygen or nitrogen. Maybe one is red, one is I don't remember the colors. So many years since I touched it. So that's now. Years ago, people observe X-ray, meaning the electrons are able to come very close to the nucleus, not just the atom, very close to the nucleus, and make interaction strong, such that it Bremsstrahlung, it emits Bremsstrahlung. And this is exactly the phenomenon which happens at the sun. The reason is that at the sun, here the density of particles is generally few particles per cubic centimeters. When you go down, it's maybe 10, maybe sometimes there is 100 particles per cubic centimeters. At the corona, it's 10 to the 10 particles per cubic centimeters. I remember the numbers. So much easier, much better there to probability to get the X-ray. About UV, there is also, I really cannot remember. Once I was dealing with it, but it was when I was young postdoc, and then I know that there is all the possibilities are valid because this is beam of electrons interacts with plasma, and they can give higher energy than visual.
Fascinating. Thank you for the answer.
Yes, there's much more than that, which is involved. That's why I called my talk as a terrestrial aurora as a laboratory, because so many effects can be observed here, and you just need to scale up to the astrophysics if you need.
Yeah, maybe there is one more question from me about this Tokamak Hawk. Can you come to the slide? So
Yeah.
there were two visions of for nuclear synthesis. Could you explain the differences? And because you mentioned that Tokamak Hawk is more easy, how about the second option, stellar rotor? Is anybody implementing stellar rotor now?
Yes, in Germany there is
Yes, yes.
research stuff.
Tokamak was kept secret in 54, 55. Russians were keeping, that's why it's called. And 57, I think it was in one of the meetings, they decided that plasma physics will not be classified matter. Also, I cannot remember. That's why also 58 became the first geomagnetic year, when the special conference, and there were Russians and the Western together the first time met. And then tokamak is simpler. You can see the picture is very simpler. The problem is how to avoid the walls. Can you see here the walls? Because making such a device is quite simple. You can do it. But making such a device that would withstand hot plasma, which you need MEV in order to make nuclear reactions, MEV plasma, such that fast ions will not hit the wall and destroy it, or make the confinement impossible. So there he brought, and I am once, when I was a student, I was thinking about going into fusion. So this would be the nice picture of magnetic field, etc. And this is supposedly all what I know, what I remember, that this is easier from the point of view of confinement. But to build it is much more complicated. But I must say add something else. There's another method which is very, very important, and it's done a lot. And this is laser. You take a small ball, pellet, it's called, a tiny, I don't remember, but it's probably micron, size of micron. And you inject a strong laser. And what does it do? In theory, if you do it from two directions, maybe from 4 directions, it will get pulse, an energy pulse exactly at the outer part, and will cause immediately shock wave, which will go inside. And as the shock wave, the radius is decreasing, the curvature is better. As it's the radius is decreasing, it becomes more dense, and eventually it's so dense that nuclear reaction starts. So this is a great idea. This is called inertial confinement. Inertia meaning by force you do it. When they did it, when I was student, they started already talking about it, I would say more than 30 years ago. And the lasers were already there, and then they found phenomenon which were unknown, which is like a good but bad. They found a lot of plasma physics, a lot of interaction, new waves appear. The laser, the non-linearity of the laser caused so many beautiful and complicated phenomena that the pellet itself could not sustain itself. But 5 years ago, they finished to build in Livermore, not far from here, 10 years ago, another device which has the same purpose, but it has 200 lasers from all directions, exactly with the accuracy of picosecond. From many points of view, it's beyond imagination. Meaning huge lasers, 200 of them, exactly 192 for some reason, emerged at the same time. And they were sure that they already announced that 2030 will have energy. Well, it didn't work either. It condensed the matter, started, but nature is fickle. So that's my point is that as what say, I don't know to start saying some famous person, I will tell you once, who said, if it's bad, it's good. Because if we don't succeed, but it's so interesting that we shall get funding for research as a job.
All right. So maybe three more comments from Dr. Jarek Duda, because he makes some comments in the chat.
Okay, so some comment that there are more approaches, but I'm not sure if how successful they are for fusion. So one is, for example, that there are these lasers. There is polywell. So polywell is that you make some cube, make of six coils, and the electron should travel to these coils and make some fusion in the center. So it is developed for many years. And another is dense plasma focus. So that they have some short circuit like, and that has created sometimes singularity like situation. So they also claim to get fusion, but the efficiency is not great. And also there is this general fusion company which uses mechanical approach, that they have this kind of hammers which simultaneously struck at the center, creating shock waves, and in the center of these shock waves they want to get fusion, but I don't know how well it goes.
Yeah.
So this one, yeah.
That's correct.
There are many approaches, but I don't know which will win finally.
I don't know if you heard about 20 years ago, maybe more, 25 years ago, there was the big revolution, big
Cold fusion, yeah.
about cold fusion.
Yeah.
And people started to believe until it was proven that it's not precise.
Yes. But so these are hot fusions, but different approaches. And they say that they see some fusion, but the efficiency is below 1. Łukasz has a question, comment.
Yeah, so please go ahead.
Yes, I also wanted to ask one question about the exploration of different auroras in our solar. Oh, sorry, different Łukasz.
Yeah, so different Łukasz. Dr. Stemping, please go ahead.
I'm sorry, these names matched.
Okay, thank you very much. I'd like to thank very much to Professor Roth for very inspiring and very interesting talk. And my question is about the possibility of appearing of solitons in the systems described by you. What is the possibility of appearing of soliton waves or solitons in plasma in these situations which you are talking about, which we are talking about?
Yeah, thanks for the question. I love this topic. There are two items. One is the soliton, as we learn from differential equations, which is a localized feature which propagates. General, yes, it's not surely it's not really wave, and I would say the following: 95% of analysis in plasma physics, I described I sketched some description how you couple equations Maxwell with Boltzmann are essentially looking at waves. Surely there we observe and we know that plasma sustains nonlinearity, and then dispersion can be balanced. The simplest way, dispersion can be balanced by nonlinearity, and then you get solitons, what people call solitons, like the Lord, the British Lord who was in England 200 years ago or so, and so on the water. Forgot the name of the scientist who got the equation first. There's also nonlinear Schrödinger. So that's clearly. And you ask if they are observed. Yes, they are not so popular, not observed very often, but surely they must exist, and they do exist. Observation in space, it's extremely difficult from this point of view, because you have to be at the right spot at the right time. Because if this soliton comes, it's not repeated, it's not a wave. It's not. Then there is another aspect, which I can talk about it more, about solitary structure, meaning that that is what they call solitons, or solitary structure. They are essentially some kind of localized feature which have specific topology, and they are observed definitely. I can give only one recent example. 3 years ago, we launched an amazing satellite which goes into elliptic orbit around the sun, but really close to the sun. So close that, just give you an example, we are now at the Earth, we are in distance of 220 solar radii. It's about 150 million kilometers. So 220. Light reaches sun in the distance of 12 solar radii. Just was there last month. And he observes very weird structures which are not very well explained by simple plasma physics linearization. So bottom line is, there's a future, big future to solitons in plasma physics.
Yes, many thanks. Thank you very much. Thank you very much.
Yeah, so I guess there's no more questions. So we have quite extraordinary long discussion time. We already discussed for like 20 minutes or something like that. So I guess since we have no more, do we have more questions or? Yeah, I guess all questions were already given. Okay, so Professor Ilan Roth, thank you so much for participation and for giving this seminar. I mean, and for bringing this scientific spirit. I know this is quite late in your place, right? It's like 1:30, right? At
1:35. 1:35.
Yes.
Instead of reading or watching something pleasant, I had to listen to myself. That's not.
All right. Thank you so much for giving the seminar, and let us hope to meet in some time in future. Thank you so much for participation.
Bye.